Hello, today we're diving into a fundamental concept in mathematics, rates of change. By the end of this video, you will be able to distinguish between average and instantaneous rates of change, use them to describe how two quantities vary, and compare how fast a function is changing at different points. Our essential question for today is, how can we compare how fast a function is changing at different points? In other words, if we have a function, how can we tell if it's changing quickly or slowly at a specific point on its graph? This question is at the core of calculus and has endless applications in the real world. Let's start with our first objective, understanding the average rate of change. Think of a road trip. You might drive 300 miles in 5 hours. To find your average speed, you would divide the total distance by the total time. That's exactly what we're doing here. The average rate of change of a function f over an interval from a to b is given by the formula. The quantity f of b minus f of a, all divided by b minus a. This formula tells us the constant rate that would produce the same overall change in the function's output over the interval from a to b. Let's see this visually. On a graph of f of x, we can plot the 2 points, a f a and b f b. The expression fb minus fa is the change in the vertical direction, the rise. The expression b minus a is the change in the horizontal direction, the run. We can connect these 2 points with a straight line. This line is called a secant line. Notice that its slope is exactly fb minus fa over b minus a. So, a key takeaway is that the average rate of change is simply the slope of the second line connecting 2 points on the graph of a function. Let's try an example to make this concrete. Let's find the average rate of change for a quadratic function. F of x equals x squared over the interval from x equals 1 to x equals 3. Our function is f of x equals x squared, and our interval is a equals 1 to b equals 3. First, we need to find the function values at the endpoints of our interval. At the start of the interval, when x is 1, f of 1 is 1 squared, which is 1. At the end of the interval, when x is 3, f of 3 is 3 squared, which is 9. Now we can plug these values into our average rate of change formula. The average rate of change is f of 3 minus f of 1, all over 3 minus 1. This gives us 9 minus 1 in the numerator and 3 minus 1 in the denominator, which simplifies to 8 over 2. So our final answer is 4. The average rate of change of f of x equals x squared over the interval from 1 to 3 is 4. What does this mean? It means that, on average, for every by 1 unit increase in x epi of x increased by 4 units over this interval. It also means that if you were to draw a line through the points 101 and 309, its slope would be 4. We have now seen how to calculate the average rate of change, fulfilling our first goal for this part of the lesson. Now let's move to our second objective, the rate of change at a point. While average rate of change gives us a big picture view, the rate of change at a point, sometimes called instantaneous rate of change, is about what's happening at one exact moment. Think of your car's speedometer. It shows your speed at that precise instant. But how can you calculate change at a single point, where there is no interval? The answer is, we can approximate it. We can get closer and closer to the exact rate by calculating average rates of change over smaller and smaller intervals. Let's return to our graph of f of x and look at a point. Let's call it P. If we pick another point Q and draw a secant line between P and Q, its slope is an approximation of the rate of change at P. Now, imagine moving point Q closer to point P. As we do this, the interval becomes smaller, and the secant line gets steeper or flatter, aligning itself more closely with the curve at point P. In the limit, as Q merges with P, the secant line becomes what we call a tangent line. The slope of this tangent line is the rate of change at that exact point. So the rate of change at a point is the slope of the tangent line at that point. This is the central idea behind the concept of the derivative, which is a major focus in calculus. We've now established our second key understanding. Rate of change at a point is found by taking the limit of average rates of change, resulting in the slope of the tangent line. Let's work through an example to approximate the rate of change at a point. We'll use the same function, f of x equals x squared, and let's find the rate of change at the point x equals 3. We've already established that the average rate of change over a larger interval can approximate this value. Let's start with a small interval around 3. Let's choose the interval from x equals 3 to x equals 3.1. This is a very small step away from our target point. Now we'll use the average rate of change formula. The average rate of change over this tiny interval is f of 3.1 minus f of 3, all over 3.1 minus 3. Let's calculate the values. F of 3.1 is 3.1 squared, which is 9.61. We already know f of 3 is 9. In the denominator, 3.1 minus 3 is 0.1. This gives us 0.61 divided by 0.1, which equals 6.1. So the rate of change at x equals 3 is approximately 6.1. What if we choose an even smaller interval, say from 3 to 3.01? We would calculate f of 3.01, which is 9.0601. The average rate of change would then be 9.0601, 0.01, which is 0.601, 0.01, or 6.01. Notice how as the interval shrinks, our approximation gets closer and closer to a value of 6. This suggests the true rate of change at x equals 3 is exactly 6. This process of getting closer and closer is how we use average rates of change to find the exact rate at a single point. Next, let's address how to compare rates of change at two different points. Our third objective is to understand how we can compare the rate of change at two different locations on a function. The method is straightforward. For each point, you'll find the rate of change and then simply compare the resulting numbers. Here's the process. First, choose 2 points. Let's call them A and B. For each point, you'll compute the average rate of change using a small, equal-sized interval around it. Finally, you'll compare the two values you found to see which is greater or if they are equal. Let's apply this to f of x equals x squared. We want to compare the rate near x equals 1 with the rate near x equals 3. We've already found an approximation for the rate near x equals 3. Using an interval like 3.1, we calculated an average rate of change of 6.1. This suggests the rate at x of 3 is around 6. Now let's do the same for x equals 1. We'll use a similarly sized interval, say from 1 to 1.1. Calculating the average rate of change, we get f of 1.1 minus f of 1 all over 0.1. This is 1.21 minus 1 divided by 0.1, which is 0.21 divided by 0.1, or 2.1. So we have an approximate rate of 6.1 near x equals 3, and an approximate rate of 2.1 near x equals 1. Comparing these two values, it's clear that 6.1 is much larger than 2.1. This means the function f of x equals x squared is changing much faster at x equals 3 than it is at x equals 1. This method allows us to quantitatively compare how rapidly a function is changing at different parts of its domain. Our final topic concerns how two quantities vary together, which helps us interpret the sign of our rates of change. A positive or negative rate of change tells us about the relationship between the quantities we are studying. A positive rate of change means that as one quantity increases, the other quantity also increases. They move in the same direction. On a graph, this looks like the function is rising as you move from left to right. For instance, if your speed is positive, then as time increases, the distance you've traveled also increases. Both time and distance are increasing together. A negative rate of change means the opposite. As one quantity increases, the other decreases. They move in opposite directions. On a graph, this appears as a function falling as you move from left to right. An example might be the remaining amount of gas in your tank during a long drive. As time increases, the amount of gas in your tank decreases. They are changing in opposite directions. So, the sign of the rate of change is not just a number, it's a description of how the two quantities relate to each other. We can also tell how fast a function is changing by looking at its graph. The steeper the graph, the greater the rate of change. Think about two hills. A steep hill is harder to climb because your elevation is changing rapidly for a small horizontal distance. A gently sloping hill is easier because your elevation changes slowly. The same principle applies here. Let's quickly recap the key takeaways from today's lesson. We started by learning that the average rate of change over an interval is represented geometrically by the slope of the secant line connecting 2 points on a function's graph. We then saw how the rate of change at a single point, also called the instantaneous rate of change, can be approximated by finding the average rate of change over very, very small intervals. Geometrically, This is the slope of the tangent line to the curve at that point. We also saw how the sign and steepness of the rate of change describe the relationship between the quantities. A positive rate means they move in the same direction. A negative rate means they move in opposite directions, and a steeper graph means a faster change. These concepts of rates of change, secant lines, and tangent lines are the foundational building blocks for calculus. They help us understand and describe the world around us, from the speed of a car to the growth of a population. Thank you for watching.